Today we are going to look at a new class of functions called rational functions. And a rational function is a function that takes the form f of x equals a polynomial divided by a polynomial. And that's where the idea of rational comes in, because it's a ratio between two polynomials. An example of this is 3x plus 2 is divided by x to the power 4 minus 5x squared plus 7. As you can see, the numerator is a polynomial of degree 1 because the highest power of x is 1, and the denominator is a polynomial of degree 4 because the highest power of x is 4. But first of all, let's point out that we're going to only consider functions of the type linear over linear. So our rationals will be restricted to simple cases where we have a linear in the denominator and a linear in the numerator, such as f of x equals 2x plus 3 divided by x minus 1. That's as far as we'll go. First of all, let's look at the parent function of the rational functions. It is given a special name. It's called the reciprocal function. And as you might expect, it looks like so. F of x equals 1 over x. Where is the polynomial in the numerator, you might ask? Well, this is a polynomial of degree 0, because the highest power of x in this expression is x to the 0. That's why you get a 1. And this is a linear in the denominator, so it's a polynomial of degree 1. So let's see how we can draw the graph of f of x equals 1 over x. Let's begin by the old-fashioned way of taking a table of values. F of x equals 1 over x, and obviously you know that f of x equals y. So when x is negative 4, y is negative 1 over 4. When x is negative 3, y is negative 1 over 3. And again, negative a half and negative 1. What about when x equals 0? Obviously, we'll end up with 1 divided by 0, and that's not allowed. So we do not have a value of the function at x equals 0. And actually, you should know this, because when you look at this function, you know that x does not equal 0, and that we have a domain restriction in this case, as we've done this before. So the function is not defined at 0. Let's see what happens at x equals 1. The function equals 1. At x equals 2, the function equals a half, then a third, and finally a quarter. So let's see how these points look like on a piece of graph paper. And here we have our negative points and our positive points, but then it doesn't look very clear. So we'll say, let's look at more points. Let's investigate what happens when we take further points and see how the shape develops with this. So let's say that we will take a value at x equals, let's say, negative 10. And in this case, y would be negative 0.1. And if x is 10, y is 1 over 10. Let's take further values between negative 1 and 0. When x is negative 0.5, y is negative 2. And when x is negative 0.1, y is negative 10. Similarly, when x is 0.1, y is 10. And when x is 0.5, y is 2. So we have a few more points to plot on the graph. And now, this is our graph. When we add the extra points, this is what we get. Note that you have the point corresponding to 0.1, 10, and 10, 0.1. The same applies to the negative values here and here. And obviously, at x equals 0, we cannot have a graph because the function is undefined there. So if we connect the points, that's what we get. This is the general shape of the reciprocal function. Two curves, two separate curves, but they represent the same function. It's not connected, and they appear in diagonally opposite quadrants. Let's ask the question, if the curve of f of x equals 1 over x touch or cross the axes. The question, can x equal 0, implies that if it does, then the curve crosses the y-axis. But we have seen that x equals 0 is not allowed. It's a domain restriction. So this does not happen, and this implies does not cross the y-axis. Furthermore, we can ask, can f of x equal 0, i.e. can y equal 0? If this is the case, then you would cross the x-axis. But let's consider the expression 1 over x, which is the value of our y. Can this ever equal a 0? No, because for a fraction to equal 0, the numerator must equal 0, and in this case our numerator is 1. True, as x becomes very large, the fraction y becomes very small. For example, when x is 1,000,000, y is 1 over 1,000,000, which is very small, but it is never equal to a 0. So this implies that the curve also does not cross the x-axis. If we look at the curve, you'll find that the curve really does approach the y-axis as x becomes very small, and the curve does approach the x-axis as x becomes very large, but it never touches or crosses. And those two fictitious lines are called the asymptotes. This is the vertical asymptote, and an asymptote is a fictitious line that the curve approaches but never touches and never crosses. And in this case, this is the horizontal asymptote. In this case, the asymptotes coincide with the axes, but this is not necessarily always the case. Let's keep in mind that the vertical asymptote is associated with division by 0. If you look at the curve here, it's where x equals 0. So 1 over 0 is what generated the vertical asymptote because it's a domain restriction. However, the horizontal asymptote is associated with extreme values of x. We are approaching the asymptote as x becomes large in the positive or large in the negative. That's why 1 over x becomes very close to 0, and that's why you approach the x-axis. So to sum up, the curve f of x equals 1 over x, which is called the reciprocal function. It is the parent function of all rationals, and it can be sketched simply by drawing the axes and drawing two curves that represent the function, and we have a horizontal asymptote in this case and a vertical asymptote that both coincide with the coordinate axes. The vertical asymptote coincides with the y-axis, and the horizontal asymptote coincides with the x-axis. And finally, you might say that when you look at the graph, for example here, it seems as if the curve is really touching the axis. But then, this is the problem with the pixels on the screen. Let's look at this and let's zoom in, and we will find that there is a distance. So what happens if we go further up? We can do this process, and then it might appear that the curve is really approaching the axis and that it really does touch the axis. So somebody would say, hang on a minute, it looks like we're touching the axis here. So let's zoom in again. And if we do that, we will find that no, the curve does not touch the axis. And we can keep on doing that forever and ever. So this is the idea of an asymptote. The curve is approaching the axis, but it will actually never touch it.